And what we are going to look at is this second slide now. First thing to see, a useful function to define models that have changes of concentrations over time, so-called Michaelis-Menten rate equation. It comes under various disguises. It's also found in surface catalysis in a similar way, and the essential component that it has compared to mass action kinetics, and you find all this explained in the materials, is that it is a saturating function, right? That unlike mass action kinetics, this Michaelis-Menten rate law predicts that even though you can have huge amounts of substrates for an enzyme, if you have a finite amount of enzyme, it will only be able to convert substrate into product at a finite rate, at a maximum rate, and it can't be faster than the case when all the enzyme works at its maximum speed. So the highlighted in yellow here is the actual formula. So the rate is given as a constant called Vmax times the substrate concentration, and it's divided by the Km or Michaelis constant plus the substrate concentration. And this denominator gives us the saturation properties that converts a linear function into a hyperbolic function. And we see that it's an easy way to calculate the actual rate with which the enzyme works. However, we have to bear in mind that this is based on assumptions, right? That this looks very simple, but it's actually based on a couple of assumptions. And then whenever we apply it, we have to make sure that these assumptions are actually fulfilled if we want to use this rate law. For example, one of the assumptions is that the enzyme concentration is much lower than the substrate concentration, which might be the case if a substrate is glucose and the enzyme is a glucokinase, but which might not be the case if we have a protein kinase and the actual substrate is another protein. Then these concentrations might not be dissimilar, and in that case, the Michaelis-Menten law would not be applicable. So that's, as always, we have to check it. And another important restriction is that this is derived for one-way reaction, an irreversible reaction. And of course, all chemical reactions are in principle reversible, and particularly enzyme kinetics is mostly reversible, so we would not trust that this works in all cases under, for example, in vivo conditions. Anyway, our slide shows a figure of the two authors of that original paper where this is all based from. And if you look at it a bit more closely, this paper is actually from 1913. It's a rather old paper. It's more than 100 years old by now. And it's still a very, very fundamental paper. It's simple, but it has not lost any of its strength since that 100 years that have passed. In the middle of that figure shows Victor Henry, a French physical chemist, where Maud Menten and Michaelis actually say that they took the idea of this simplification from him. So it's mentioned in the paper, and that's why we also show him in that figure. So let's look at this function in some detail, and for this again I switch off the webcam. And we go back to our MATLAB. And I hand over to Rob.
Hello everyone again. Okay, so this is the Michaelis-Menten scheme. I don't think we had that a second ago. So actually substrate plus enzyme going to an enzyme substrate complex. That can also degrade back down into the substrate plus enzyme, or catalysis can happen and product is released from the enzyme.
Right, we have to refer to the materials for an explicit explanation because we only take the final result, which is the Michaelis-Menten approximation to this more complex mechanism.
So we go through a quasi-steady state, what's called a quasi-steady state approximation in order to get this final single equation out at the end. So in this equation we have two constants and the concentration of the substrate. So Vmax, which is equal to the catalysis rate, kcat, times by the amount of enzyme, the concentration of enzyme, and Km, which is a constant derived from effectively the rates taking you away from the enzyme substrate complex, so K backwards plus kcat, the catalysis rate, over the forward rate, so of production of the enzyme substrate complex from the original equation.
Right. So this is the derivation of that mechanism, which leads to this simplified version of a rate equation that we can use as a good first step to calculate rates.
So the first thing we need to do, of course, is to translate this into MATLAB code.
Yeah, what we are going to do is we're going to look at this function, and particularly after we have looked at this function, generalize it then to the more general Hill equation and look at the function of that, look at the properties of that Hill equation.
Okay, so we're going to use anonymous functions again with their at notation. So an at with brackets. Inside the brackets, we need the parameters to the function. In this case, we're going to have the concentration of substrate, Vmax, and Km for the two constants. And then we just need to define the function itself, so Vmax times S over brackets Km plus S. And I hope you agree that's exactly the same as the rate equation here. Okay, so I think we want to have a little look at what this looks like, don't we?
Right. If we want to look what this function looks like, we can use it directly, but remember that Vmax and Km are things that we need to specify. So how can we do this?
Well, what we want to do is work towards using the fplot function, but fplot expects a function that only has one variable, not S, Vmax and Km, but just S. So let's make a new function called mm1, which takes one variable, S, and then of course we can call our original function mm. We still want S to be specified, but now we need to set Vmax and Km. So I'm just going to choose, say, 1 and 0.1.
So these are now arbitrary values, and we'll comment on how to get these values a little bit later in the code.
Okay, I'm just making sure we get a new figure. Let's pass it that function that I've just defined, mm1. And of course, again, some limits, 0 to 3, say. Okay, if I run this. Aha.
Make it bigger, we can see the hyperbolic function as expected. The saturation function starts with a linear growth for very small substrate concentrations and then levels off to approach the value of, well, if you look at the derivation of the function for very large substrate concentration, it should be approaching 1, because you set Vmax equal to 1, and we can see that already at a value of 3 for the substrate concentration, we're getting pretty close.
So I'm going to add in some labels just to make this even clearer. We want the substrate concentration, and the Y label is the rate. If I just run this, okay.
Right, then we have substrate concentration horizontal axis from 0 to 3, so we have just chosen a certain range, so that could be, for example, millimolar if it was a conventional metabolite, and then the rate would then be expressed as the change of concentration per unit of time. And of course, it depends how you define your Vmax and your Km, and the Vmax will then define whether you have that expressed in conversion per second or per minute or per hour or per year.
So if you recall, we specified two numbers. The Vmax as 1 and the km as 0.1. So this means that our rate has a maximum of Vmax, a maximum velocity of 1. As you can see, it's approaching 1. It will never go higher than 1. And the km is the point at which the half maximal rate is achieved. So 0.5 in this case is just about 0.1. You can just about see it over this side.
Okay, so if we pick that value where the rate is 0.5, then we can see where, yeah, we can guess it's near 0.1 in that case, but we can check if we change the value. What did you do? You changed km to 0.5.
Here, and I added a different color in.
And now you run the function again. You get a new plot. And if we look at the half maximum value now, it's exactly at 0.5, as you can. Visually, at least, it's derived, and we can even calculate it. I think we did that in one of the previous sessions, that you can actually also calculate this. And all the functions, all the properties of this function, of course, are now accessible to us.